So, in the first lecture, we looked at elastostatics in 1D. And well, I will go very briefly on what we did last time, just as a recap. So we look at the one-dimensional problem. If you remember, this was a bar, which can only sustain traction or compression. And then we said, well, what are the forces that are acting in an infinitesimal element of the bar? And then we said that there is the actual force, right? And it has a different value at both ends of the bar because, well, maybe there is some sort of load per unit length that we also apply. We use that, of course, because when we take these to higher dimensions, that B is going to become the body force, like, for instance, the weight of the body. And then we looked at all these forces, and then we said, well, if I want to have elastostatics, so I have to basically apply Newton's second law, and so the sum of forces, in this case, is equal to 0 because the bar is at rest. And so if you do that, you take the limit as the infinitesimal length goes to 0, then you get basically the proper definition of the derivative. And so when you plug in what is the value of the force, remember that force is equal to the stress multiplied by the area. And if you assume that you have linearity, right, between stress and strain, so you have Hooke's law, then all of that is basically EA du dx, right? So we have our strain is our simplest strain, right? If you remember in the nonlinear mechanics course, we were looking at high order strains, but for the purposes of this class, everything that is material and geometric nonlinearities are going to remain linear because the advanced features of FEM are going to be in different aspects, okay? So when we plug that in, we found that the governing equation is basically d dx EA du dx plus B minus SU is equal to 0, and this had to be valid for every single point along the bar. Now we said that this alone is not enough to set the boundary value problem, right? You need, in addition to that, you need boundary conditions, right? We can integrate that equation twice, and then integration constants are going to emerge, and those can only be defined by boundary conditions. And so we looked at 3 different kinds of boundary conditions. I told you, I knew it. Okay. So 3 types of boundary conditions: essential or Dirichlet, natural or Robin, and then you have the mixed one. Natural or Newman, and then you have the mixed or Robin boundary conditions. These are the 3 types. And so we said that the displacement along the bar was going to be our primal variable. Of course, when we say primal, in this case, we're looking at elastostatics, and so the primal variable is the displacement field. But in other problems, like, for instance, heat conduction, our primary variable is going to become the temperature, right? And so then the natural is on the dual variable. In this case, is the actual force. And so the mixed or Robin boundary condition was a combination of the 2. Okay, then we said if we have the governing differential equation and the boundary conditions, we have pretty much everything that we need to set up properly the boundary value problem. If not, we don't have a well-defined boundary value problem, right? And so we said, well, we're going to state it as given all these quantities, right? We need to provide, of course, the Young's modulus, the area of the bar, the spring, the load per unit length, and all these things have to be provided, right? So the objective is to find U, right, that has to be smooth enough so that our governing differential equation is satisfied, but it has to be satisfied at every point along the bar, right? And of course, we have boundary conditions to set up properly the boundary value problem. And so since we have 2 ends of the bar, remember that we had to impose these boundary conditions in pairs. We could have, for instance, a prescribed displacement on gamma u and a prescribed actual force on gamma t, or we could have prescribed displacement and a prescribed Robin boundary condition on gamma r, or it could be a pure Dirichlet problem, a pure Newman problem, a pure Robin problem, and so forth, all possible combinations, but we have to enforce this in pairs. Okay, so there is a big problem with this formulation, right? And the problem is that satisfying this equation along the bar, point-wise, right? For a 1D problem, it may be straightforward, But when you take to higher dimensions, these formulations, right, it gets impossible, right? It's very likely that you are not going to be able to obtain an exact solution. And so what we try to do now is we try to relax this requirement that it has to be satisfied everywhere point-wise. Maybe we don't care so much about that. And so we are going to cast this problem in a different way. So the purpose of today's lecture is to look at weak also called variational formulations. Okay. So what we do is we take our differential equation. You already know this from the nonlinear mechanics class. And then we say, well, we're going to multiply that by some function that we call a weight function or a test function. We're going to integrate that over the domain. And then we're going to say that that is going to be equal to 0 for all test functions in some space of functions, right? We're going to talk a little bit about what the space of functions. But for now, let's say that is going to be called the energy space, right? Yeah?
What is the upper bound?
L. So that is the length of the bar. We're integrating over the length of the bar, right? And so this is the energy space. So what does that mean? Well, we're going to define it because, of course, you can take functions from different spaces, and yeah, it's for us to decide what would constitute a proper space of functions to use, right? But for now, let's define this as a set of functions that have finite strain energy. So first set of functions V such that U of V, which is defined as, well, my energy for the bar is going to be defined as 1/2 of EA dV dx square plus SV square that's a set, right? What we have here, this quantity, is my strain energy. Okay? And the whole idea is that strain energy has to remain finite. That's it. I mean, we're going to use functions so that in a way our strain energy doesn't blow up. Because obviously there is no reason to have strain energy that is infinite, right? What happens when the strain energy is too high? It breaks, right? So from the point of view of a problem in elastostatics, right? The moment our strain energy becomes infinite, well, something went wrong and our bar breaks. So we're going to just use functions that have finite strain energy. And that is what we call the energy space. So it's a very simple definition. And of course, in terms of, like, in practical terms, it doesn't make sense to have a function that at some point in the domain goes to infinity, obviously, right? Because we also have issues integrating these functions, right? And so we could potentially have problems for which the function goes to infinity at one point. And we will talk later about this class of problems, right? Those are more difficult problems to solve, okay? And theory tells us that those problems, when we use the finite element method, they converge at a lower rate, okay? All right, so we normally say, when we define a function space, we say, well, that energy space is going to induce a norm, and we need a norm, right? Because we want to be able to measure things in these spaces, right? The same way as if you have an Euclidean space, and then you define the norm of a vector as basically the distance of that vector, right? I can say that basically the distance of that vector is the square root of the magnitude square, right? So I can dot that vector by itself. We have to do the same thing in energy spaces, okay? So that we can measure things. Because then later, well, how do I know whether a function is good enough, right? I should be able to measure things, and if I'm going to do convergence analysis, I need to know how that quantity that, for instance, I measure as the error goes down as I refine the mesh. So we need to be able to measure things. So we normally say, well, my energy space induces the norm, and I'm going to call the norm of V, which is a function again, measured in the energy space, is going to be defined as the square root of U of V. So essentially, I'm defining this. It's a definition. So I'm saying that the norm of a function is going to be the square root of its straight energy, right? And that is essentially a definition. And I'm going to use that to measure things in functional spaces. So similarly to the way we measure things in Euclidean spaces, as we discussed, now we have a way to measure things in functional spaces, okay? Now, there are many, many similarities between these two. I'm not sure whether you guys have experience in the past or you have dealt with function spaces, but there are many similarities, right? So we can measure things in Euclidean spaces. Now, by a simple definition, we can measure things in functional spaces, okay? All right. Okay, but yeah, this form, keep in mind that what we're saying here, right? What we're saying here is like, okay, I don't really care anymore about that being satisfied pointwise. Remember that this is going to lead later to our discrete system of equations. And then by choosing a proper function space, let's say polynomials, the way we do it in finite elements, we accept that most likely we're not going to get to the exact solution. And so there is going to be an error in the approximation. But we say, well, that function is not going to satisfy pointwise, but on average, this function is going to be satisfied, on average. And I will be happy with that. Why will I be happy? Well, because I know that I can get a sense of the error that function is causing, right? And if I see the error and I can control it, then I'm in good shape, because in the end, I get a solution. It may not be the exact solution, but it's good enough for engineering purposes, okay? So that is the whole point. But we cannot really work with that, so we do integration by parts. So if you remember integration by parts, and our equation is u dv is equal to uv minus the integral of v du. So if we do that, and I only want to do integration by parts on the first term, and I want to do that because I see that the equation as is, it has a double derivative on u, right? And there is no derivative on w. So we do integration by parts to balance the order of derivative there. And something interesting is going to happen when we do that. So if I do now integration by parts on that term, so w d dx ea du dx dx is going to be equal to this w multiplied by, well, let's du dx evaluated at 0 and L minus the integral of this, and then I have dw ea du dx. Yeah? And something interesting happens here. The moment I do integration by parts on that term, you notice that something pops up. What is that? The boundary conditions pop up, right? And we looked at also at the all of this in the nonlinear mechanics class, if you remember. So this term here, ea du dx, is simply the axial force. And now I need to evaluate that at 0 and at L, right? So basically, by simply doing integration by parts and by balancing derivatives, because now I have a single derivative on the test function and a single derivative on my u function, right? Now those are balanced, and this has nice features. The balancing of those derivatives, in the end, is going to lead to nice properties in our system, right? our discrete problem is going to have nice properties, and this symmetry here in the formulation also leads to symmetry in the resulting stiffness matrix and so on. We have nice properties. Okay, so now we're going to put that back into the main equation, and so you have 0L EA, and then you have du dx, dw dx plus WSU is going to be equal to the integral 0L WB dx plus WEA du dx, again evaluated at 0L. And that, of course, we said has to be valid for all test functions, all of them, in some properly chosen space that for now we're going to call again the energy space. So we're going to say hello. We're going to call this here B of U W, and this whole thing that we have on the right hand side, we're going to call it L of W. And you will normally find this expression all over the place. We try to cast the problem in abstract form, and we say the weak form is going to be stated as find U, right? Again, belonging to that energy space. We want U, which is going to be the exact solution. Keep in mind that I'm still not in a discrete problem, okay? I have not reduced the dimensions, so still I'm living in an infinite space. So still these functions are not useful for the purpose of finite element analysis. So I want to find U, and that U has to have finite strain energy, right? Such that now I say my B of U W is equal to L of W for all test functions in the energy space, right? This here is the so-called bilinear form, and on the right-hand side you have the linear form. Bilinear because this whole thing here depends on both U and W, and on the right-hand side we have only things that depend on W, okay? And you may argue, well, but I see here on the linear form I have du dx. Well, keep in mind that this whole term here on the right is actually going to be replaced by the boundary conditions, which is something that we know a priori. We know the boundary conditions, otherwise the problem is not set up properly, okay? And so this here is actually not unknown. So it does not depend on U, okay? So keep that in mind. Okay, well, let's list some nice properties. And again, this is the problem, the weak formulation or variational formulation cast in abstract form, right? And well, for our particular case, which is the elastostatics problem in 1D, well, it just happens that the bilinear form is written like that for our case, and the linear form is written like that. But when you move to other problems, you can always state the variational form in this way, right? It's just that the bilinear form and the linear form are going to take different forms, right? They are going to be different expressions to it, but still you can cast that problem in the same way, okay? All right, so let me talk a little bit about these properties, because if you take, for instance, functions U, V, and W that belongs to some space V, and you take a scalar C. Hi. No problem. This bilinear form has many nice properties. So we can state that the bilinear form is greater than or equal to 0, right? It's only going to be equal to 0 whenever these functions U or W are equal to 0, right? Everything is 0. But otherwise, it has to be greater than 0. Then we have a nice symmetric property. You can see that B of U and W is equal to B of W and U. And indeed, if I just look at every single term in this expression, right, if you just swap the two, you get the same equation, right? If I put here W and here U, and I put here U and here W, it's exactly the same expression. So there is this nice property that is symmetric. And that does not happen for all problems, right? There are problems for which that symmetry is lost, okay? But for this particular case, remember, we're dealing with elliptic equations, differential equations, and so for those problems, we have this nice property of symmetry. Then you have another property, that the distributed property, so you say B of U plus VW is equal to B of UW plus B of VW. Distributed property, right? And then finally, we can actually use that scalar CUW is equal to C times the bilinear form applied to UW. And well, these nice properties, eventually you can actually use them in the formulation to try to manipulate terms here and there, maybe come up with an alternative formulation. But it is important that we state them. Yeah?
Does this also mean that if you have in the lowest property, if you have, for instance, B, CU, and then CW, does that imply C squared B? Okay.
Yes, correct. It does.
And the commutative property, that's the second one, doesn't always hold in larger dimensions.
In larger dimension, it holds, as long as the problem remains elliptic. But there are problems, for instance, when you're dealing with advection problems, for instance, right?
Yeah.
That doesn't hold anymore. Yeah? So that's why I'm saying that as long as the problems are easy enough, like elliptic differential equations, then this property should hold. And again, these right now, again, it's a little bit abstract, but eventually when we move to the discrete system of equations and you can really see the structure of the problem, you can see that now our stiffness matrix is going to become symmetric just because of this nice property, right? Okay. Now, if we compare, if we take a look at our bilinear form, right? We look at this expression here. This is our bilinear form. And now you look at the way we have defined our strain energy. What do you see?
Sorry, can you ask it again? The question?
If you look at my bilinear form, right? This is my bilinear form. And then I look at the way we have defined strain energy. What do you see? Huh?
It's scaled by half.
It's scaled, but it's pretty much almost the same, right? So just by comparing these two expressions, we can get a relationship between what would be to measure something, because remember that we're using our strain energy to measure things in these functional spaces, right? And then our bilinear form. And that's what I want to do now. So compare the bilinear form with the strain energy. And we basically, if you take my U is equal to 1/2 of B of U comma U. Notice that I need to put, instead of W, I have to put U to make it really a scale version of the strain energy, right? And so if we look at the way we defined how to measure things in the energy space, now I take the norm of U in the energy space. That is essentially going to be equal to the square root of 1/2 of B U comma U, right? And again, I just simply go back and I look at the way I have defined the way we measure things, right? So if I now put U here, and I put U of U there, and I know that U of U here is going to be 1/2 of my bilinear form, then I can now measure things by looking at the bilinear form. And this is very interesting, right? It's very interesting because now I know that the bilinear form is going to lead to a structure of my discrete system where the stiffness matrix is going to be that left-hand side of the equation, right? And now I can measure things using that. I can use the bilinear form and the resulting stiffness matrix to measure things in these functional spaces. And so, for instance, give me a second. For instance, if instead of u, I can now put the error with respect to an exact solution, now I should be able to plug in here b of error, comma, error. Error is going to be u minus u exact, for instance, or uh minus u, right? And now I am able to measure the error with respect to an exact solution. And that is great, because if we can measure the error, we know exactly how we are doing and how our approximation is going to improve as we reduce the mesh, and we can do convergence analysis and all these great things that we can learn about the finite element method. You have a question?
Yeah, so the question is actually, so if you look at the form of B, U, and U, and then previously we had the bilinear form of B and W, does this imply that W becomes more restricted? Because in effect you actually equate W to U then, right?
Yeah, but we're going to talk about that a little bit in the next lecture, because what happens is that the Galerkin projection, who took my nonlinear class? Okay, you guys remember what I said. The Galerkin projections to me is one of the most incredible inventions in mechanics, because what it does, I'm saying this equation has to be valid for all test functions in a space, all of them. And then, well, you may argue, wait, well, just pick any function, right? Well, it turns out that the Galerkin projection ends up picking the test function that gives the least error in the approximation. The least error, which is something, to me, is really, really crazy. So from all these functions, I take the test function that makes the error the smallest. And there is a theorem that proves that in the book. It's called Sia's approximation theorem, right? And you can see how that works. It's a very simple mathematical proof, but then we can use this as S, right, to figure out what would be the error in the approximation. Yeah.
If I remember correctly from nonlinear,
yeah.
If we look again at the weak formulation, the Galerkin projection manifests it in the dot product between the test function and the rest of the rest of the expression, right?
Mm-hmm.
To ensure that as in Euclidean space, it will be like the dot
exactly.
product.
Yeah, we will talk about that in the next lecture. All of that, and we're going to make an analogy. So of course now we have more time than in nonlinear mechanics, and so we're going to spend a little bit more time talking about that, how incredible that property is. And we're going to make, again, an analogy with Euclidean spaces, because we can see things in Euclidean spaces. But with functional spaces, that becomes very hard. But before we go there, let me just finish, because we still need to solve a little issue. And it's how do we deal with non-zero essential boundary conditions. And there is a little subtlety here that we need to discuss that we did not discuss in nonlinear mechanics, simply because we don't have the time, right? We cannot cover really finite elements in 4 lectures. But now we do have the time. So now let me finish this, and then we're going to talk about the Galerkin projection. So for non-homogeneous, basically non-zero, essential boundary conditions, given u is equal to v plus some u tilde. So I'm going to now express my solution u as the sum of 2 functions, one that I call v and one that I call u tilde. And u tilde, right, I define u tilde so that u tilde does satisfy the a priori the essential boundary conditions, right? So that where this u tilde, so actually the restriction of u tilde on gamma u is equal to my u bar, which is the prescribed displacement, right? So we do this trick, right? So that essentially in the end, what I'm left, since this is something that I know, and it prescribes the Dirichlet boundary condition, then I am left with a part of the function that I don't know. And this function is going to belong to the same space as the test function. So this v, which is part of the solution, the unknown part of the solution, and the test functions are belonging to the same space. That's the trick we do, right? So if we do that trick, then the objective is, of course, find v that belongs to v naught such that, and I will define what that V naught is in a second, such that V of u w is equal to L of w. Remember, that was our original expression for all w in V naught, and I say this explicitly. I want you to understand that this is the same space, so I have to find this V, the unknown part of the solution belonging to V naught, and then the V naught shows up also again there, so I'm taking these functions from the same space, right? And of course, if I now replace what u is into my bilinear form, then I have only the unknown part V minus B of u tilde w.
Certain question.
Yeah?
So V would be another trial solution in the same energy space.
Yes, that is our trial solution. And so, notice what happened. U shows up here, but I know that U is this, right? So by the distributive property, we can express that as the sum of two bilinear forms. And notice that because U tilde is something that I know a priori that satisfy the boundary conditions, right? It basically goes to the right-hand side. It's not a function of the unknown anymore. So essentially, what I want you to see here is that if you have a problem for which there is a prescribed Dirichlet boundary condition, right, that somehow later is going to modify my right-hand side, which is my force vector, right? So a non-zero Dirichlet boundary condition is going to do something to my force vector on the right-hand side. And it makes sense because it's something that I know a priori. So everything that we know a priori about the problem, remember the boundary conditions were also modifying the right-hand side, right? Everything that we know a priori is going to have some effect on the right-hand side of our problem structure, okay? Okay, but what is that V naught? Well, V naught is basically a set of functions V that belong to the energy space. Again, we are only interested in functions that produce finite strain energy, such that V evaluated at gamma u is equal to 0. And obviously has to be equal to 0, right? Otherwise, we have a problem. If this guy u tilde already satisfies the boundary condition, well, obviously, this V here, evaluated at that location, has to be equal to 0. Otherwise, there is a problem with that U tilde, yeah?
Couldn't there be an error so that the V doesn't equal it's not equal to 0 per se?
No, we normally do it equal to 0. But there was another reason why. You remember nonlinear mechanics? Why we said that we were going to take functions from a space that was, the value was equal to 0 at Dirichlet boundaries. Do you know why? Because the reaction, remember, we didn't like dealing with the reaction. That was the other main reason. So basically our formulation simplifies and one of those terms goes away just because we like dealing with these functions that go to 0 there. Does it have to be? No. You may have something. Now we have an issue because if I say, well, now I want V that does not go to 0 at Dirichlet boundary, right? Well, but now I have an issue there because now U tilde no longer satisfies the Dirichlet boundary condition, right? So in order for me to figure out, well, I need to evaluate this whole expression, right, at the location of the Dirichlet boundary. And then you have more issues because you need to keep in that term that contains the reaction in the formulation. You need to do the integration, and that is going to end up showing somewhere in your discrete problem, and it's a problem to deal with that, right? Okay. Any questions up to this point? Okay, let's stop here. And then we continue with the Galerkin projection in the next lecture.